let's continue with the last talk of the day. So it's Federico Raimondo, researcher at Forschungszentrum Jülich.
Don't speak German, but close by.
Close by.
Research
German.
center.
All right. So we'll hear about the do's and don'ts when it comes to applying predictive modeling, both in big data sets, but also in smaller data sets.
Yeah, so thank you for the invitation. Indeed, I'm a computer scientist with a PhD in computer science / cognitive neuroscience, and then I moved to do some postdoc in more clinical applications. But in the end, I came back to the origins, and now I'm doing applied machine learning within the Neuroscience and Medicine Institute in Jülich. So I'm going to change a bit the topic of today. In the morning, we have some computational models. Then we had some networks, time-varying functional connectivity, and I'm going to talk about machine learning in general. So is any one of you planning to or applying machine learning in your research right now? Okay, quite some hands up. That's good. So I'm going to just show you some things. And if you don't raise your hands, think if you ever did BCA or ICA in your research, and then going to rethink why you just lied to me. So I'm going to go for a brief introduction just to have everyone on the same level. So maybe it might look a bit basic. I'm going to go through some examples, but then I will show you some of the problems we're facing with machine learning in general that is contributing to the reproducibility crisis that we are having, and hopefully convince you to do things properly, whatever that means. So when I talk about machine learning, is because we want to tell the computer to find some rules given enough examples. And these examples could be examples that have a label. This is called supervised learning. And then we have examples that we don't have a labels. That is called unsupervised learning, also known as clustering. And what we work is mainly here, I'm going to talk about tabular data. So we have our X. We're going to see it through the presentation, which is our list of samples. And the columns will be the variables, the predictors, whatever we're going to use to predict our target label Y. And when we talk about learning, it's because we have our data, we fit it into a learning algorithm, and then we end up with what we call a model. And the idea of this model is not to explain us the data, but to actually predict what would be the label on new data. And I'm going to come back to that later. So if you want to build a machine learning model, there are very simple 2 steps that you have to follow. The first one is to build a model, and the second one is to build a successful one. And it might look like this is a joke, but it's indeed not. Because if on the first attempt to build a machine learning model, you nailed it, 100% accuracy, you can distinguish whatever you wanted to distinguish, then maybe your problem was too easy, and you didn't need machine learning for that. So that's one attempt. The other one is like, okay, the first model I built is not that perfect, okay? But then maybe you have an easy problem. Keep trying, maybe you can make it better. So it's not about building one model, it's about building several. And this is what we do in machine learning. We keep trying. We have our data, we have our predictors, our variable to predict, and we keep trying to. So the first question, in case we have an easy problem, is something that I ask all the time whenever somebody comes with a machine learning problem. Is like, why are you using machine learning? Like, do you really need machine learning for this? And it's quite easy to just follow a path or follow a direction, just not go back to the beginning and say, okay, do I really need machine learning for that? So normally we use machine learning because we have 2 conditions. One is because the task we perform it routinely. So it's something that we're planning to do several times. And the other one is because the complexity of the task or defining the rules on how to do this is way too complex for us to explain to a computer. We cannot come with an algorithm to tell the computer how to do the task. So basically, we just say, okay, I have this data, I want to build this, Just you tell me which are the rules for it. And this is mostly what happens in neuroscience with complex multidimensional data, talking about MRI, MEG, PET data, and combinations of it. And the other reason why we might want to use it, because maybe the rules that we have now do not apply in the future. Think about, for example, spam. I had an email account in the 90s, and I received spam emails in which there was always a Nigerian prince that had millions of dollars to give me because I was in their inheritance in Argentina. And then now there are lots of people that want to publish my book about the last paper I published someday, and they're fascinated with it. Or they invite me to this conference where you pay a lot of money, just go, and everyone happens to have a bad picture of them that is all stretched. So yeah, the data changes. So if we devise the rules and then the next day the data changes, we don't want to think again and make the rules again. So we use machine learning because there is adaptation. Or we simply have more data. We have more and more data, we want to make our models better. So that's why we use machine learning. And again, counter examples of machine learning, when we can come up with the rules, there's no need to do machine learning. Just put the if then, even if there are a lot, just like take your time. Building machine learning models is way more complex than what you think. So this is like machine learning in general, but why do we want to do it in research? The same reasons that we had before, but now, since we're researchers, we just don't let the model do the job. Then we want to say like, okay, but why the model learn? I mean, like we're stubborn, we want to know, we want to be the holders of the knowledge, not the computer. So we will start asking the model, what is it that you have learned? Because I couldn't. So I want to be superior to the computer, so I will start interrogating the model until it gives me the answers. And this is where I thought like, okay, this is the good topic for an interpretable brain data workshop, because machine learning by itself, it is not. So here is where I will add another keyword here, because most of the time we confuse them. And one is explainability. And the explainability is the ability to link the input and the output of the model. So it's whatever we put in the model as predictors and whatever the model predicts, we want to see, like, for example, the areas of the brain that contribute to defining which patients are in minimally conscious states or unresponsive, that I will talk later. So I want to see which areas of the brain or which electrodes in the EEG are capable of decoding my earpiece. This is explainability, it's not interpretability. Interpretability is a bit more complex. It's talking about the human interpretation. Can we really give an explanation of why biologically this is happening? What is the cause and what's the effect? And you will see a lot of papers about interpretability and explainability in machine learning and in AI in general, how it is needed, and yet this is a big problem. And I found this illustration that makes it nice for me to explain why everything is explainable. Because even if you have a very deep neural network, you can still see all the coefficients and how your data is transformed from input to output. You will have like thousands of operations, but you can still be able to explain. Who will understand that? I don't know. Don't come to me to explain what your neural network does, because I don't have enough time to go through all the math. And I don't have enough mental capacity to follow presentations where we have too many equations. I had enough in computer science. I went in the other direction. That was my limit. So this is where we start dealing with interpretability and explainability. On this side, we have, these are all names of computational learning algorithms. And we see here the neural networks are less interpretable, but they're still explainable. And then there is a gray area, because here we have the logistic regression, we have the decision trees, but that also depends on the kind of data you put. Because if you put the whole brain volume of fMRI time series in a machine learning, and then the model says, yeah, I look at this voxel in this time point, and I made the decision based on that, what can we explain on it? We don't even know what that time point represents in the time series. We need more information. So it's also about what we put in the model. So since everyone was showing, like examples of their work on how they apply machine learning, I will also do the same thing. This is one of the papers I did. One possible application of machine learning in research is when we want to classify patients, group of patients or group of populations in which is kind of hard to distinguish. These are patients that wake up from coma. These are healthy controls, but the thing with this, at least these two group of patients here, is they're patients that they open the eyes, but they cannot communicate. Normally, you will know them as patients in a vegetative state, but they're more than just the vegetative state. Johnny mentioned a bit about it. We have the minimal response, minimally conscious. Here is the second column, and this vegetative state. And this indeed was not my paper. This was a paper that my PhD director published. And then he said, like, okay, I build a machine learning model. I say, I don't believe you, but we have more data. Okay, build another one and tell me whether it still sustains. So what I did in my PhD is I automated the process, extracted the same markers, and built yet another model so to confirm the results, including what I mentioned before. This is new data. When he published, he used this data. I trained his data, and I managed to predict the new data with the same accuracy. Move on. Then he said, like, okay, but there is more information about consciousness. It's not just in the brain, there is also in the heart. So I added some ECG extracted markers, and I showed that the accuracy of the model goes up by a bit, but it goes up. So there are some more information there. And if you don't care much about classifying patients, there is another way of doing supervised machine learning, which is regression. This is a figure from Shami Moore from our group. This is age prediction. So you have the chronological age, and then you have the brain age as predicted by a machine learning classifier. This has been done. There is a lot of work, a lot of literature on this problem because it also applies to neurodegenerative diseases. The moment that your predictor gives you an older age than your actual chronological age, you consider that's brain delta, and it's also information that there is something wrong there. I'm not going to go into details. Check the literature. There's many about that, mostly by Cole working on this kind of problems from different kind of features. Another application is MEG, or this is EEG, but MEG more or less similar. Do the coding. We do the coding to see whether we have an ERP, event-related potential, or event-related field. This is, for example, an auditory paradigm that distinguishes the MMN from the P300. If you don't know, it doesn't matter. If you know what it is, it might be important to you, but the idea is that we train a model for each point in the time series, and then we test it in all of the other points in the time series. So we have a two-dimensional plot. Each value here is one machine learning model, and what it tells us is how these patterns sustain across time. So if the pattern 100 milliseconds after the stimuli is decodable, fine, but is this the same pattern that decodes at 200, 300? So you can see how this is sustained. This is work from Jean-Remy King and Stanislas Dehaene. If you want to see more about this, this is another application. I use it to compare ERPs within different stimulation modalities. This is auditory, somatosensory, and visual. These are the mismatch negativities using 3 kinds of stimulations. And then this is the P300, which is related more to working memory and conscious processing. So we could see different patterns, but patterns that were more sustained in time. This was expected, but then we started doing the cross-decoding of things. So if I can decode an MMN, auditory MMN, can I also decode the somatosensory MMN? So we tried all of this, and this is work done with Maria. She was in Cambridge back then. So we tried all of the combinations, and we could see small patterns that were kept. Of course, this is EEG, so we cannot really pinpoint to where it is. But if you know anything about the MMN, the auditory MMN, you know that it happens in the auditory cortex. So why is the somatosensory and the visual having similar patterns of activation? Mr. EEG, great to do with an MEG. I think it's impossible to do that setup. The paper is longer than this, has many good results. We also tried the global effect, and they were all very similar. And this is something that also is known because it's the processing, the conscious processing should happen in the same way. So these are examples of why we can use machine learning in research. But as I said, we don't stop there. We usually do one more step. So now we have 3 steps to do machine learning in research. One, we have model, build like successful, and then we learn from the model, because we are not going to stop that. We just want to keep learning from machine learning to see what is it happening in the brain. So I have 2 questions for it that I will try to answer today. The first one is, what is a successful model? because I'm not saying a perfect model, I'm saying successful, and then we can have different parts to what we feel it is successful, and then it's up to us. And the other one is like what is that we can actually learn from the model, because we might think that we can learn whatever the model learned, but there are some restrictions to which scientific claims we can bring from a machine learning model. So I will start for the very basic. What is exactly a successful model, or how we can test? Just to clarify a bit, the real goal of machine learning, at least supervised machine learning, is not to learn a representation of our data, is to learn rules that will apply later. So we have our training data, but then we have testing data. And what we care is that these labels are correctly predicted. This is how, but we don't know it. If a patient comes to our clinic and then we use a machine learning model to diagnose the patient, we don't know the label. Or if this patient is at risk of death, we're working with this right now. This is a real example. We need to be able to predict if the patient is at risk of death. But if we say it's not, and then it dies, we made a mistake, but it's too late for us. So we need to be very clear on what is the goal of machine learning, and this is the real goal. Now, whenever you see a result for machine learning, it's because somebody already had labels. So what you're actually seeing is what we call cross-validation. So we take our data, we do shuffling or not shuffling or whatever you want to do, and then we split it in what we call the training data and the testing data. We use the training data to learn the rules, and then we take our validation data, we ask for the predictions, and then we see whether they match or not with our real labels. We compute an error, we can compute as many metrics as we can, and then repeat this process because maybe the random partition of the samples doesn't work, or it's like fixed and it gives you a higher value than what you expect. Now, the problem is this, that when we do this, we tend to repeat it and repeat it and repeat it. And every time we repeat it, maybe we decide to change something in there. Like, okay, let's change a parameter of, or a hyperparameter of the SVM. Let's change the way we process the data. Let's change the Schaefer parcellation because we don't want to use 400, we use 200, and then let's put the subcortical structures. Okay, let's add functional connectivity to it. So what happens is that we keep repeating this, and we are getting knowledge, because if we add the functional connectivity and doesn't work, then we remove it out. So this is what we call leakage. And what happens is that we're adding information from the testing data in the model. We know. And if we repeat this too much, we're going to have an overestimation. And there is no way for that. And whenever we have an overestimation, we're going to learn rules that apply specifically for the training data. And then we're going to do scientific claims based on that. So the first step is to know that if we repeat this too much, we're going to overestimate them. And you won't have any problem right now. But I've seen papers that they published, and later on, when we try to apply to the same data or new data, the same models, we cannot reach the accuracy that they published. Our accuracy is lower. And it has two potential impacts. One personal, like the person that actually built that, it's like, I'm not going to trust you anymore with your models. And the second one is like you set up the bar, because I will show you how we define a successful model, but the next one coming, it needs to make a model that works at least like that. So whatever you try, you need to reach that accuracy. And if you want to publish a new model, you need to be better. And if you make something that you publish and it's okay, 95% accurate, because you made a mistake and it's impossible to detect, the next one needs to come with 96% model. And sometimes it's very difficult. We are having troubles with it. So the first thing is that we overestimate. And the thing that I learned a lot working in an institute full of biologists, psychologists, physicists, but engineers, but people from computer sciences or elite experts in machine learning, which I'm not, is that we also overestimate ourselves. And this is the first mistake I did. We think that because we learned how to drive a car, we know how to fix every car. So I built my first successful model, and I thought, like, okay, great, give me data, I will keep building models and models and models per machine. Like, I will solve all the problems. Now, I built one successful model. The moment I was with another problem, just a tad bit difficult, no, I need some help. And then at the beginning, I thought I was here. This is a slide. This is the group leader. That's the PI from our group, Kaustubh Patil. I thought I was here like the person that could actually diagnose every problem and come with a solution. Now I've just built one model. I was the person that could actually drive a manual and an automatic car, and that's it. So then after a lot of training, I still do not believe I'm on that side, but my take is to not overestimate your knowledge. And this I've seen it, not master students, not PhD students, I've seen it on PI. So this is the most difficult part, because then you go into an argument with them, like why it doesn't work, and then it's like it's complicated to convince them. So my take, if you're having trouble with your machine learning model or not, check. Because if you're not having troubles, maybe it's like I said, the problem is too easy, or you're doing something wrong and you're overestimating your real accuracy. And why am I mentioning this? Because building machine learning models is not about building one. Like I said, we're building many. And why we need to build many? Because we need to choose many options. We have learning algorithms, and learning algorithms have hyperparameters, which are ways of controlling the learning processes. And then we need to select something. So the problem is that we have our data, we feed our data, we put it into the learning model, and the learning algorithms, when you ask the question, have you learned? They will say, yes. No matter what you go, they will say, yes, I learned. But then it's like, okay, this is like kids in high school. Okay, did you learn? Did you study? Yes. Okay, and we do a test. And this is what we call the training error. We just test the model on the same data we used to learn. And then like predict the labels. And what we're going to find, usually, is a curve like this. When the model is too simple, so the complexity of the model is low, the error is going to be high. But whenever we start adding complexity to the model, the training error is going to be very low. And this is because highly complex models are capable of memorizing data. So you just put, I don't know, 100 samples on your training data and a very, very complex model. And then you ask each one of the 100 samples what are the labels, and the model can give you exactly that answer. But this is not the real goal. What we want is the goal, the value of the test sample on data that the model hasn't seen. And the problem of why we're building many, many machine learning models is because the other curve on the testing error looks like this. So what are we looking for? We're looking for this star. And this is what we're all the time looking. And that's why we build model after model after model after model, because we want the model that minimizes the test error, but we don't have infinite test data. And this is the problem of building machine learning models. So what we always come is for an estimation of where the star is. And this is what we need to estimate properly. So how to choose models? Well, there are many ways, mainly doing repeated cross-validation, not too many times. Then we calculate some metrics depending on what we're interested in. Some metrics are going to be more difficult than others to optimize. And then if we have two competing algorithms, we have other quality attributes that we want to check. For example, interpretability. If we have a deep learning network or a very simple decision tree that more or less gives you the same answer, maybe stay with the simpler, just because of interpretability, because it's something that is going to be more useful than just a label. That is, depending on the accuracy of the model, maybe sometimes 70, 80, or even 60% accurate. So everything goes to model fitting, model selection, and actually choosing something. So we're all the time comparing. And I'm going to show you that even though we try to come up with statistics, we can always cheat them. So it comes to the reader. And if you don't plan on doing machine learning, but you actually read or listened a talk about machine learning that all of the talks had, we need to be a bit skeptical of what we're seeing, or at least check the details to see if things are correct. The first example of how we can make two models look like I created a successful model is because I'm comparing to something that is completely stupid. This is a chance level. This is a dummy classifier. This is a classifier that makes prediction based on the distribution of the data. Nothing to do with the predictors, but the variable. So if we are predicting, I don't know, male and female, and we're 50-50, it's just a 50-50 prediction. When we measure the balanced accuracy, it gives you a perfect 50%. And this is a model that on average gives you 60% accuracy, so 4 out of 10 are wrong. I don't know if it's a successful model or not, but if we do this comparison, we have a p-value, and clearly this is the winning model. Excellent paper. I don't know. I wouldn't trust this much. And so the reality is like, we try more than one. And here I just changed the support vector machine for a random forest, and I got 70% accuracy. Just 10% accuracy, just by changing the learning algorithm. I didn't do much. And this is like out of a machine learning tutorial. You can find this to try 2 or 3. So if we see something like this, check, because maybe the authors did just more than these 2. And this one is one of them. Or what does it really mean to have a 60% accurate model for the problem at stake? The other one is some sort of like p-hacking. For example, here I did the 10 splits cross-validation. No? So I split it 10 times in different training test sets. I have 2 models. This is 70% accurate. This is, I don't know, 70, almost 72. In the Kruskal-Wallis test, Wilkinson test, p-values are not significant. Okay, my model is not better. Let's say I made model 2. My model is not better. Okay, let's do 500 splits. Same test, same model, both of them almost 70%, p-value here 0.003. So my model is better. Really. So if I give you a plot like this, you will see that maybe you don't believe me. But if I just give you the statistics and the accuracies without or the standard deviation of this, you will actually believe that model 2 is better than model 1. Then the same model. But it's not different. And there is but this is just because we just repeat the cross-validation too much. We're just running it for longer, generating more samples. And it will happen. I mean, 500 was for these 2 models. Sometimes with 50, it's okay. I wanted to find 2 models that are like very, very much the same model. And then the other one is because there is a corrected t-test that I will show later that actually comprises in the formula the number of repeats and the number of the samples in training testing, and this will give you also a value that is not significant here. So there's a better statistical test. And we'll come back to that later. And if you don't believe me that this can happen, yeah, this happened. This is done of neurology, impact factor more than 10. I'm not killing anyone, this is me. They asked me for a statistical test. I did it. I will show you later. Indeed, I showed you before the original figure submitted to the journal. There were no statistics there. The number of iterations were fixed already because it was a random number. It was bootstrap, cross-validation, but they asked me for a statistical test, so I had it. It's like, it's meaningful, it's meaningless. I'm not going to discuss with the reviewer. Here you have statistical test, doesn't mean anything. There, of course, they were significant. And I mean, these 3 models were the same. These 2 models were different, and this model was different. That's it. It's there in the points. And then I mentioned about the statistical test. This Nadio, Vengio, this is good people, but it's still hackable. This is the only formula in the presentation, I promise. So here this is the traditional t-test of 2 population of means of paired t-test, because we always have the same prediction from the same samples. So this is the mean of the difference minus the expected value. Here is 0, and the standard deviation of the difference divided the square root of the number of samples. So what they propose is to correct for the number of tests and the number of samples, but if we can actually manipulate this, we can change the t-value. And so I did a very simple simulation. I have 2 models here. What I did is, instead of splitting the data into 70-30 or 60-40, I split it in all the options. From 10% of the data for training and 90% for testing to 90% for training and 10% for testing. The 2 models, they're different. The p-values, no. The moment I reach 50-50, yeah, the p-value is significant. Before here, they are not significant. So we can manipulate this if you want to. So we can have a p-value we want. So the message is not that we cannot use p-values or we cannot use this test, but we need to be skeptical when we read. If there is something odd, something non-standard in the way that this data is split for cross-validation, maybe there is something fishy there. Traditional tests, there are more tests. There is 5x2 CV test, there is the McNemar test. There are several of these. There are like ways of doing cross-validation. One is called K-fold, and normally we do a 5-fold, 5 times repetition, or a 10-fold, 10-time repetition, and that's it. If there is something weird with these numbers, sometimes to speed up stuff, we put a 3 instead of 5, but just to make it faster. The results shouldn't matter depending on the number of splits or the repetitions and everything. They should be the same. It's not a factor. It's the way we evaluate the generalization error. But if there are something that is non-standard, okay, don't look at the p-value, look at the actual result. So, okay, half an hour into it. Now that we have, let's go finish, okay, with the first part. So, did I answer what a successful model is? Unfortunately, in the current practice, it's a model that is above chance level or better than the literature. And this is why I mentioned that if we overestimate it, we're not only putting ourselves in an uncomfortable position when we come years later and our model doesn't work, but we're also making the rest of the researchers working in the problem to find issues publishing, because it's not about building the models, it's about publishing them. Because if you read something that is in the same level of accuracy of another model that was already published, many people that are not, or reviewers that are not in the machine learning domain, they won't allow these papers to go, because it's like, why you spend so much time building a model with something that you already solved with the same accuracy? So it's kind of hard on the domain we're working on. So for the next 15 minutes, I hope, let's try to answer the other question. First of all, we need to build a successful model, because whatever we learn from the model is going to be bounded by the accuracy of the model we build. If we build a model that is 51% accurate, that means that out of 100, only 51 are correct, which is above chance level, according to that, then whatever we learn from it is learned about this extra person per 100 that we managed to classify correctly. So this is the same work before. These are the same models that we built with Dennis Engelman therefore to predict dog patients from one dataset in Paris. But here is another plot, which is a plot of the feature importance. And this, if you read any paper about using machine learning for something, you will see something like this. It tells you like how much is the contribution of the individual features to the overall classification or the model or whatever you're doing there. And we show that in this paper, it was quite easy. We show that there are connectivity markers in the theta band, entropy markers, and some spectral variables, alpha, theta, mostly, involved in consciousness. And then we tried, since here we have event-related potentials, in this data set from another clinical center where I did my postdoc, they didn't have evoked potential because it was resting state. So we trained the model in Paris. We tested in this with only the resting state markers, and we found that the usual suspects were already there. Permutation entropy in theta, and spectral power in alpha and theta band, as well as connectivity in theta. So something relevant for the people that are interested in consciousness. What we learned is exactly that patterns during task generalize to rest. So even if you're doing a task, we can still classify consciousness from those patterns extracted there into resting state. We also did in this paper several analyses on what happens if you have a different EEG montage of the recording, shorter is longer, whatever you do, still generalizes. And the most important variables are from mixed kinds, mostly information, connectivity, and spectral. This is what we claim in the paper. Okay. The other one is the one that this is the original figure without the statistical test. I showed that if you have ECG in the features, they perform better, meaning that there is partially independent information in the ECG compared to the EEG. That's it. That was the plan. Another example of this is MEG in sleep. This colleague of mine, Melanie Strauss, came and she said, like, you know, that N1 and responsiveness, we tend to put N1 all together like it's one thing, but there are many things. There is the classification of Hori stages. That is from 1994, and she tagged all the subjects that were on a MEG during a whole day trying to do an active task. Poor people. They fell asleep, of course. And then she tagged every 5 seconds this data. And then she found that, for example, here in D3, which is also 8.5, We have responsive trials and non-responsive trials. So what she asked me is like, okay, but are these different brain states, are the same brain states? Can we actually predict from the ongoing activity if the subject later will reply in this stage? So I started, of course, building machine learning models. I built one machine learning for wakefulness, one for H1, H2, H3, H4, and 5, and then we ran out of data. So it's like there were very few people in deep sleep replying to the command. And so what we actually found is that we were able to decode some better than other. H5 was quite good, H1 was not, more or less like that. But the question was like, okay, but are the patterns the same? Is this the same state or the same pattern that I can discover in wakefulness, the same one in H1, H2? So I started to test the models on different stages, and what we found is, for example, here that the one for wakefulness was able to decode more or less not so good in H3, H4, and finally was quite good in H5. And I did that for all of these, or thousands of models in the end, because I trained different learning algorithms. But the question is like, okay, but why is this happening? So again, let's go and dig into the feature importances and see what I put into the model. And it happened that for W and H2, H3, H4, H5, there were some features that were always present there, some kind of report that this is the top 6. I didn't plot all the 60 that we had, except for H1, that H1 was not able to classify neither of the deeper stages. And this is because they were, the model was looking at specific features from H1. But it's not only about the features, but also the pattern in those features and the relation between them. So what we learned, that patterns are embedded in other states, some of them depending on what you see in the results, and mostly due to shared important features. But that's it. We cannot claim more. And why we cannot claim more? Because we might have collinearities. And let me show you an example. This is simulated data. This is not simulated data. This is the iris data set. So if you do a data science tutorial on Python, you will find this. These are flowers, 2 species, and this is the length of the petal, and this is the length of the sepal. If we fit a support vector machine, it gives you that line here, almost perfect classification. And then I look at how the coefficients of the SPM are, and then we see that, of course, from the plot, you can see that the, this is in the other wrong screen, you can see that the most important here is the petal length. That's the most important variable, and then the sepal length adds a bit, but not that much. So if we look at the 2 features, this has a coefficient almost -1 absolute value, but this one is coefficient of 3. But what I did is like I started adding variables correlated to the petal length, 1, 2, 3, 4, 5 until 10. And then I tested what happened with the coefficients. And if we see here, the coefficient for the petal length started going to 0. Then the darker colors are with more correlated variables. These are highly correlated variables. But the sepal length, they started here and started going higher. So if you actually look at sepal length, it becomes suddenly a very important feature compared to the rest, but the rest are all the same. And the same happens if we look at other metrics, because you can tell me like the SVM coefficients is not a good thing. Okay, let's look at the permutation important. This is a way when you actually test the model with the feature correctly and the feature permuted, and then you see what is the change. The most important feature here, when there are almost no variables added, is the petal length. And then it becomes very low, almost negative, meaning that when you actually have that feature, the model performance decreases. Doesn't make any sense. And the same happens if you use a random forest. And again, the same happens. And if you just publish one thing, when you have 11 correlated variables and 1 variable there, and you start analyzing what your variables mean and what is more important, you cannot see here poor choice of colors. I didn't have too much time to change these figures. The most important variable, according to the permutation important, is the sepal length, not all the other 11 highly correlated variables. So even if we start inspecting the models and we see and we do all this fancy analysis, we might end up drawing the wrong conclusions just because we have too many dimensions with all the same value. And this is where things become tricky, because we might see results like that, and we don't know whether there are collinearities in the features they input. But they will tell us this is the important area of the brain. While the reality is like maybe they may some other areas of the brain that they're all equally important, but in the end they cancel out because they have all the same information. So if you see something that analyzes this, unless they use SHAP or something like more complicated and complex to add explainability to the models, it's of dubious origin. Okay? So it's hard to trust all these models. I'm coming with examples to show you the problems. Of course, I'm not saying that every paper that does this has a problem, but it's also about the scientific claims. If you just show me the most important feature and they say, this is the area of the brain when things happen, no, hold on. This is not where things happen. This is where your model found pattern, but this is also linked to all of the other features. So my recommendation, use toolboxes like SHAP, which are toolboxes to actually give explainability to models that are too complex, like the low interpretability models. So you can see with this toolbox, you can have interactions between the SHAP value and the actual feature with the correlation with the other value. And here, for example, for the petal length is showing that the correlated one is highly related to this. And then you can see how they have magnificent plots. I couldn't add them here, but they have like some plots where you actually tell you how the decisions were made. And you will see that the decisions were made based on the 11 correlated values, but not because of the sepal length, even though the sepal length looks like the most important variable. Okay, so enough about adding too many features. I will show you what happens when you don't consider features. And this is like the most important, our most recent funding. Now it's like, I don't believe in machine learning anymore, almost. So this is Vera. She's a PhD student in our group. And she came to do a project predicting hand grip strength from brain images. So the UKBiobank is like 400,000 participants. They all went through a measurement of the hand grip strength along like a lot of tests. Some 40,000 of them went through MRI sessions with functional MRI, structural MRI. So we said, okay, let's build a big data model. So a lot of pre-processing time, a lot of cleaning time, lots of computing time. And she finally got some gray matter density using, I think, the 1000 Schaefer atlas and cortical and subcortical Tian and Sut atlas. And she, of course, built the model. This is the true hand grip strength here. Here we have the predictive. This is the actual, this is the identity line, and this is the correlation she found, an R square of 0.33, one R of 0.57. Good model, no? I mean, for a correlation, there are publications with 0.1, 0.2, so 0.57 is in excellent. Now, this is hand grip strength and gray matter density. Can you come up with an idea of what can affect the hand grip strength of a subject?
Age.
Age. Other one?
Body mass.
Body mass. That's a good one. We're working on it. I don't have the results for that, but we're working on it.
Yeah, work on that.
We have that. They have the body mass. They have the body fat-free mass. Or they have a lot of measurements. So the first one, let's do it binary. I thought I built two models, one for male, one for females. And here it is. Now our magic 57 became a 27 with an R square of 0.07. R square of 0 is like chance level. So yeah, not so good anymore, no? And this is because we consider them. But what happens if you don't consider? You will come with this and a good model. Indeed, what happens is that we have variables that we call confounders. And we can go into a statistical definition of that. I'm not going to go into this. We had like a 5-hour discussion with a guy in OHBM, and it's like, we call it confounders here, take it there. If you know about statistics, you want to put a name, put the name you want. But the idea is that it's a variable that affects both the features and the target. We don't know how they affect it. Linearly, non-linear, how it happens. We have no clue. So the reality here, the sex and age are confounders. And we can imagine that makes sense, like body mass is like fitness in general can also be, how do we measure that? We don't know. So she started working on this, and she made the hand grip strength only based on age, and the R was 0.15, sex 0.73. That's a very good model. Oh. In the metrics, if you see the correlation, you don't believe me much, but if you look at the statistics, that's a very good model. And then she put sex and age, and that was like the best model. So forget about the brain. Just look at sex and age, and you can predict the hand grip strength. Give or take a 5 here, but more or less. No? Not that much. This is what happens with big data. We're talking about 40,000 subjects here. And then she added, of course, she added gray matter volume, 76, cortical thickness, 77, and functional connectivity, 67. It made it even worse. So this is the kind of results that you can expect. But again, what are we missing here? I mean, we just decided that we're going to analyze sex and age. But what other things should we add? Like body mass, excellent. What else? And we can keep with the story. What about the time of the day the scanner happened? Do you know that there are differences? If you scan yourself in the morning, the functional connectivity is going to be the same or different to the one that you scan yourself after this session, after the whole workshop that we're super tired. If you make a GEG, I'm sure that everyone is in full delta now. So again, we started building this. This will come in a paper now. We're trying to finish it. It's about doing an analysis of what potentially can affect. But it's not about impeding people from doing machine learning. The idea is like, keep it, feet on the ground, think what you're going to claim. Are you going to claim that you find the neural correlates of hand grip strength, or are you going to find that you find the relationship that maybe is mediated by any other factor between the brain and the hand grip strength? That could be sex, age, or the amount of days you go to the gym, although going to the gym is not really, unless you really go and do something there. So she defined like a framework to think about this, and we have like a conceptual confound continuum in which we actually need to sit down and think what that makes sense. And if you don't believe that this is important, there are machine learning models that used to predict, for example, social variables based on the zip code, because where you live matters of what kind of health access you have, the economy, and everything. So it makes sense also that this happens for MRI scanners that you put into one place or another place. And there are differences into the MRI scanners, but because of the people that are actually scanned on there, because they come from different populations. So even the scanner can be a confound in your analysis, because you might think that this is what you're predicting, but what you're actually predicting is the socioeconomic status of the two different populations, and only if you have two. So she came up with this. You have the conceptual, this is the one that we need to think whether there might be an effect or not, and there is no free lunch here. And the other one is the statistical that we can actually test, and she tested for several of these variables. This is an example. So we have let me see if I can have the pointer here. We have here the scan time that has no effect, but then of course we find here sex that has a big effect on the hand grip strength, and this is the relation with the target, but we can also have relations with the features, and we know that age affects the gray matter density, and we know it there, but not because of the scan time. In gray matter density doesn't make sense, but when I mentioned this, I mentioned about functional connectivity. So with that, she devised this confound continuum in which you actually try to put all your variables there and then do decisions. One thing, I think I missed the slide. I don't know what happened. But the idea is you can also remove confounds. But I will show you that has some problems there if you want to. And I will point you to the reference. So in summary, first, build a successful model. Don't just stand with that model. Try to really build a successful one. Unless you reach like peak accuracy, keep digging until you're sure that you cannot do better than that. Otherwise, everything that you claim is going to be related or like limited by the performance of the model. So be honest with model evaluation for your sake, for the sake of research. Benchmark more than one, but do the proper model comparison, not just like start doing repetitions until your model is better than the other one and then you publish. Try several. And again, if you have difficulties choosing one, there are some models that give you more interpretability than others. Just like if you want to know more about the brain, keep the interpretable. Sometimes accuracy is not that important. This is what happens with doctors. Interpretability is not the same as explainability, and this might be the driver. And then after you did all that and you're sure that you have the best model, okay, you can actually learn from it, analyze it as a whole, all the features you put in, not which are the ones that are most important, but among all of them, how do they rank? If you want, use the proper tools. And of course, if you have confound variables, you can control for them. You can remove it from the target, from the variables, from the features, from the brain. I had a slide, I don't know where it is, maybe I skipped it by mistake, in which I actually show how the model behaves when you start removing the age and sex as confounds. And we are now working on it. We have some signal. Of course, it's not a 0.6 model like we find. It's like 0.2 with an XG boost and some super hyperparameter tuning. But we still now are working, like, for example, with body mass, fat-free mass as a confound to see whether fitness or some variable of fitness can help us determine the real relation between the brain and the hand grip strength. And if you decide to go on the confound removal, be careful, because there is this publication where we actually show that if you do confound removal, linear confound removal on nonlinear models, you might be actually injecting information into the model, and this will look like you actually found the model, but you're just cheating. And like I said all the time, the interpretability or explainability of the model is conditional to its performance. So as a take-home message, I'm not here to tell you not to use machine learning. Okay, just build a successful model, make sure that it's actually successful, and restrain your scientific claims to which you actually can learn from the model, not just saying that you find the neural correlates of whatever your model was trying to predict. And if you have any problem, of course, I come with a lot of problems here and zero solutions. I'm not going to leave like that. These are two libraries that we're working on. One is to do machine learning properly without cheating. We don't allow you to cheat. So even if you select some models in the plot, the statistics are still corrected for multiple comparison for everything that you tested. And the other one is to just do massive feature extraction, like if you're dealing with big data sets like the HCP and everything, and you want to start playing with parameters, because even the filter of the pre-processing on the fMRI before you do the connectomes might have an effect on your model. And this is how fine things are happening in machine learning. But if you also have a general machine learning question and you don't know where to go, we have a consultancy that is mainly our boss replying most of the complicated, but we're a lot of people doing machine learning all the time, mostly neuro. It's free, meaning that it's not only free that you don't need to pay, but we're not going to be co-authors or collaborators or anything. Just going to answer your questions, clear your doubts, come at every stage before doing the analysis, after the analysis, to check your code or to check if your analysis or interpretation is correct or according to what you found. It's there. There's a chat channel that you can also put your questions. And that's it.
Thank you, Federico. Very interesting, very informative. Do we have any questions?
Yeah, when you talk about removing the confounders, do you actually mean like removing the variance from your output, or do you mean like using the confounders as features of your model, or is it something else?
No, when you use the confounds as features of your model.
Control for the confounders, right?
Yeah, control for the confounders. When you use them as part of your model, you're actually modeling them. So you're telling the model to learn from this and what you consider the confound. So it's not a confound anymore, it's a feature. So the difference between a confounder and a feature is given by you. Everything is a variable. That's, you decide whether it's a feature that the model learns from or something that you want to remove from the model. So what we do, and this library allows you to do, is to define some features as confounds and then do a linear regression and remove that information from all your targets, from all your features. You remove the age, for example, then you have like the gray matter density corrected for age in a cross-validated way. So we know that it doesn't leak.
You linearly remove the variance of the age from the features, not the outcome or both.
No, you can choose to do it on the target. But for hand group strength, it makes sense. For classification problems, maybe it doesn't make much more sense. But it has, so far we're doing it linearly, but you can choose the learning algorithm there. It's indeed, it's another machine learning model that is trained on the confounds to predict the other, the feature, and then you use just the residuals of it. And this is what it's, we normally fit a linear regression and then use the residuals. But you can do whatever you feel like. You can configure it You can have several confound removal steps to remove sex, age, you can do multivariate. So we are working on it, although every time we found the problem, then branches, and we need 10 more PhD students, and solve problems that we are not facing them. Just found the problems by chance, and then it's like, I don't know if you are familiar with the field of computer science, but we train computer scientists have a lot of time to think of a problem and then come up with a solution to it. But sometimes they just don't care whether this problem is actually a problem, but they just created a problem. So in this case, we can start digging there, but I don't know if it's really going to lead somewhere. So we can try doing multivariate linear regression to remove multiple confounds at one, or removing them in certain order. It's a lot of running. I mean, 40,000 subjects and 4,000 features are not models that you run on a laptop.
Thanks. Really lovely. I think you shared a lot of important insights here. I'm glad you mentioned the thing about p-hacking, how we need to correct for multiple comparisons. Maybe we can toss in also always compute the statistical effect size. So, whenever you see a p-value, you want to see an estimate of the effect size, because that really tells you if the difference is important or not.
That's it. I haven't found like any literature on doing that on machine learning. Mostly the problem we have, I'm going to go back to that slide. Is because each one of these points is using some samples as training, some sample as testing. So it's not really repeated measures, but it's also not really independent. So there are some complications there. And the paper with the corrected t-test is, where is it? I don't have the date, but it's quite recent. These things are quite recent. So I haven't found anything. Indeed, when I did my paper that they asked me for a statistical test, I didn't do this because I had to code it from the paper. And it was just a review on a paper. I knew that the models were different. It was just a matter of like confirming it by coding the whole thing. And like, it's a mathematical paper. It was quite complex to just reply to one line of a reviewer asking for p-values. And I checked with colleagues. They said, okay, they told me to do the Kruskal-Wallis t-test. The Kruskal-Wallis test, some non-parametric stuff, and they put it there. It's not going to change much. But yeah, the effect sizes are important. We were just discussing this with Shoni and Shamil here, that like they come up with p-values. And when you see papers from the UKBiobank related to correlations, you will see an R of, I still remember because we're trying to decode something there, R of 0.1 or something like that with a p-value of 1e minus 100. It's an incredible value. And it's like, what happened? Yeah, you have 400,000. And yeah, the correlation is very low, but the p-value is high, and then they report it. And then I have a colleague like, yeah, we need to look at these features. Like, no, this correlation is 0.1. Indeed, we can't find anything, but we're like stuck with the literature right now because we don't have an effect size there. So I agree. Maybe we should write an email to these guys that are very good at machine learning. That's Joshua Bengio now. It's like he's on the whole we need to stop AI thing.
Maybe we can add in also how you normalize your features, or because it's an art in itself how to do.
We have a paper coming on leakage, that we call it, which is the cheating part in which, for example, let's say you normalize all your data, or your harmonization. Harmonization is a big topic right now. You have several scanners. You want to harmonize your data to have it all like the scanner differences are not there, and then you do machine learning. It's like you just look at all your data. You are violating the assumption that the testing data was not seen by any algorithm. And now we're working on all this kind, and there is a paper coming on all the kind of leakage. Like if you do a gray matter mask, even doing a gray matter mask on all your sample is cheating because you're already peeking into the testing data without knowing. So you need to do the gray matter mask. And if you do that in the cross validation, And depending on your data set size and the kind of processing you're doing, let's say you're running free surfer on it, good luck. It's a lot of computation time just to be consistent. So we usually use a data set to come up with the gray matter mask and then apply it to another data set. So we're good on that side that there is no leakage of information. But it's very tricky, and we're coming with a paper with it, with all the possible leakage that it can happen and how we can detect them.
Questions?
Out of topic, but do you agree with Benjio that should we stop AI? Should we stop AI? Do you agree with Benjio?
I don't know, but can we? I mean, I think we have a bigger problem with global warming. We know everyone, we agree that we need to stop it and we're not doing it. And AI. Yeah.
Problems which you mentioned are the same for normal GLM analysis. When you don't put these factors age and sex in, you find the same effect. So it finds correlations which are maybe driven by weather factors. The general problem is the student. So I think we shouldn't stop because of that, because it doesn't help us.
I agree. And I support with this idea. We shouldn't.
I'm not really deep into the language generation model, but it's just language or image. I mean, from there to AGI, I think it's a very big step that we're not even close, but that's my opinion without being in the field.